recording. Okay, so again, so you in this directory you can find the information for the tutorial. Is this document, and has some the what you call test cases or idealized cases for the CROCO. So use this to create your environment. So the most important thing is all dev environment, just to make sure that things work. And when you create your config.bash, you will get a directory with this. There's the content is also in the. You should have this structure, no? Your CROCO files, test cases, and all the basic things. Not different from the one we use in the coupling option, tutorial. And as it was mentioned yesterday, what do? We edit the CPP defs, we choose our test cases, we compile using job comp, we select the correct .in file that is in the test case directory. We don't have to copy to the directory where the executable file is. We just have to run it, point to that file. Once we run this case, we can copy the output will be in the same directory as the executable file. So we do have to copy the plot function that is in the test case directory to plot the result. So let's start with this internal soliton case. It's interesting that there are several analytical solutions, and there's an experiment and somewhat recent paper on this. And you can get an internal sage in this case. So what do? We edit the CPP defs. This. We search for the internal soliton case. We make sure that there's no other case that is being defined. By default, remember, regionally is defined, so make sure these are all on def. Okay. We can save this. If we look at the file and we search for what it has, so there's a paper that describes this. And we can see that the configuration for this case is somewhat simple. No parallelization, the non-bossiness, the non-hydrostatic part comes here. We have the WEN05 advection scheme that these were discussed in this morning, and everything is analytical. Okay, and it's a 3D case. Okay, that's good to know. We set the compiler. This. Now we start the compilation. And we can see that since there is no MPI, it's using the you look carefully, is using the G4tran compiler. So in the directory test cases, we will have the CROCO.in input files for all the cases. And we will see that there's one for internal soliton. So there is just one. And notice that the compilation was very fast, faster than the regional case, because there are way less options defined in the CPP devs. And this, we can also look at this. So this will be, this case will have, it's not a, they forgot to change this name. The time step is 0.2 seconds, and there will be 1,400 time steps. And it's asking for this file, but it doesn't really need it. We'll save and restart file, maybe for start again. If it finds it, great. If not, no problem. And the output will be here. Okay, let's see. So what do? I run CROCO test cases croco.in.esoliton, and it's working. So what are the latest files in this directory? This internal soliton.his. Okay, no restart. So there's no restart. It should record a restart file after 7,000 steps, but since only takes, only took 1,000 steps, that's why we don't have a restart file. So there's something not well configured here, but never mind. Okay, so we do have the file. Let's do the plotting from this screen. So copy test case plot internal soliton to this directory. MATLAB, reload libraries, MATLAB. We do start, and we do plot internal soliton voila, it works. So try this. Something interesting that you can do in this case is to change the advection scheme. I think Patrick made some comments about this, how this was could affect this distribution, and see what happens. So that's for the internal soliton case. So we can try the Kelvin Helmholtz instability. It's a classic example. Again, what do we do? We edit this file. We undef the previous case. We define the Kelvin Helmholtz instability. We compile. While we compile, we can take a look at the CPP defs. Search for here. So we can see that there's a so this is in the X direction. We can see something on the Y direction. Seems that there's a 3D case. I haven't tried it. Again, non-Bosinesque, 3D, Bueno 5 advection schemes, analytical grid, analytical everything. And is north-south periodic boundary. And that's it. So it's pretty easy. How do we run it? CROCO, test case, CROCO.in. Kelvin Helmholtz instability. Let's take a look at that. In time step of 0.3 seconds, 1,600 steps. We start, but we will not need it. Out will be in a history file. Every 400 steps of 0.3 seconds. Yeah, that's it. So semi-implicit integration in the queue. So here, remember here you can see the number of steps. This is the fraction of a day that is being calculated. This is the number of steps. So it was how many? 1,600. So we're finishing.
Andres?
Yes.
Which is the parameter of advection scheme in the first example? What was the name?
For the soliton?
Yes, for the internal soliton. Soliton, yes. Because it said at the end, try this example with different advection scheme.
Yes. So if you look for the soliton case, here's where everything is defined. And you can see that you have these advection schemes here.
Okay, thank you.
These are the ones by default that Patrick mentioned. This was like 6% more expensive than Bueno 3, but more a TSH hub. So if you do For example, you have all these other options.
Okay.
Scope 3, R scope 3, Bueno 5,
Okay.
C4. I don't know what they are, but just to show that these are the numerics. Okay, so we finished that. So now we copy from these cases, plot, Kelvin Helmholtz instability to here. Let me check something. Yeah, there's just one input file. Okay. So we did it finished already. We copy this and now we do MATLAB. Start. Oh, Kevin. And we do get these bridge blocks. And maybe something more, not remember, I think this, I mentioned this has periodic boundary conditions. So this, maybe this stops here because this, what you see here is will start coming from this other side. But I guess here, the challenge is to do an animation of this, to save several files and then you produce an animation so we can see the classical figure. And the gravitational adjustment is the third case I had in mind for today. So again, now you can see that it should be easy to do. These test cases are meant to be foolproof. They just easy to try, easy to work. So this is how it should work. So we undef this case. And this is the gravitational adjustment. And, okay, so here we can do two things. Where is it? Basin Canyon shelf. This Tucker example is also very, very interesting. It's not for non-hydrostatic, but it's very interesting. Okay, here it is, gravitational adjustment. In this case, I think this is not the default option, but you can run the non-hydrostatic or the hydrostatic case. If you want to run the non-hydrostatic, you have to define this. This is what I did. I have now. And this, what will be the difference that in the non-hydrostatic case, you have a smaller domain, 3 meters by 30 centimeters, and the pixel is 1 centimeter. So you can have very, very fine grids in CROCO if you have the physics, basically. And this is what gives you the physics for those spatial scales. So let's get this. And then let's compile this. And the thing I did found that we have to do is that the time step was giving me a CFL condition. So I had to change it to 0.1 to work. This is the gravitational adjustment, but for the non-Basinesque. So I think you have to change this to 0.1. And this one, normally there's 1,000 steps. I have to add 2,000 steps. 0.1 second every step. Yeah, okay. CROCO, test cases, CROCO.in. Gravitational adjustment, but the non-Basinesque, non-hydrostatic case is working. Meanwhile, I copy from test cases the plot gravitational adjustment to this directory. I open MATLAB and it's 2,000 steps. Start, plot, gravitational adjustment. And I do get these plots. These are different time steps where you can see these instabilities developing in the interface. And remember, this is a vertical range, is 30 centimeters. And this is 3 meters at 1 centimeter scale. The pixel is 1 centimeter. That is impressive. But if I want to do the hydrostatic case, the classic gravitational adjustment case, no, overflow. Adjustment. I just remove this and this line, this keyboard, save, compile. This case, okay. And to run this model, I use the other .in file, the normal .in file. What? Why are you doing this to me? Oh, okay, this is wrong. I didn't. This should not be activated. I made a mistake somewhere. Let's see, this is. Oh, so I didn't. Sorry, I forgot to save it, I guess. Oh, it's compile without that. This is what we did before. And now we will run it in the normal case without with the hydrostatic. This is the hydrostatic case that does work. And when we do the file, the output file will have the same name as this one. And if we plot, we use the same script. And we see this classical gravitational adjustment case where the vertical range is 20 meters here and 60 kilometers here. So is this figure. So this is a classical animation in fluid dynamics. So you can now, with more steps, you can do it by yourself. And these are the reference for each of the cases if you want to study the papers.